I want to continue our discussion of reactions now to a concept really important in chemistry, which is the concept of reaction stoichiometry. And what this is really a fancy word of saying we're interested in how to quantify, how to measure the different amounts of reactants that we're going to use in a reaction, as well as how much product we're going to get. So, stoichiometry is originally it's a Greek word. It means to measure, but really, what how it applies to us in terms of way chemistry works is it really has very practical uses. So some of the examples of the reason we care about stoichiometry is listed here. When we make something in chemistry, when we run reaction, we'd want to know how much products we're going to get, right? That's would be something that's super critical to know. Do I get a lot of products? Do I get a little bit of products? Specifically, how much, right? How can I quantify that products? Of course, the other thing that's really important is, well, how much reactants do I actually need to make that product? I need to go buy some of these reactants. I need maybe to make some of these reactants. So how much of them is needed? And if something goes wrong, how much do I actually make as a result of it? Did I make, let's say, I'm supposed to make 20 grams of material, but I only end up making 10 grams. Is that good? Is that bad? Right? So those are measures that we need to have in order to tell whether the reaction we're running is efficient or is not efficient, and how we can improve it. So all of these are related to the idea of reaction stoichiometry. Now, the concept itself is actually not difficult because it's very much related to how we do things when we're trying to either cook or bake, or prepare anything really in the kitchen, or even like if you're trying to make drinks, for example, like cocktails or anything else where you require some kind of a mixing of different components, right? So the example I gave here, the analogy I gave here is a baking analogy, where here I say to make 5 pancakes, I'm going to need 1 cup of flour, 2 eggs, and half a teaspoon of baking powder. Okay, so that's my recipe. And the way you can think about this is on the left side, I have my reactants, and on the right side, I have my product. And the numbers, they're given there, 1, 2.5 here on the reactant side, and then 5 on the product side. Those are really my coefficients, my stoichiometric coefficients in a chemical reaction, right? So when we look at all of these chemical reactions from, the prior section, we can see that those numbers really are just the same as these numbers right here, which is the numbers for our chemical reaction. And then the different ingredients that we listed in our baking recipe is the same as all the different substances that we have in our chemical reaction. Okay, so that's the first thing to just get across is you don't need to be necessarily intimidated by reaction stoichiometry. The reason I say this is because a lot of students are, because they see a lot of math that we're going to get into in terms of calculating things. But the basis of it is similar to, like I said, cooking or baking, making drinks, and so on. Okay, so now the next thing we need to understand is just when we're given a recipe like the one I circle here, what does that mean? What is that recipe telling us? Well, it tells us a few things, right? It tells us that, if I have 2 eggs and a bunch of all the other materials, I'll be able to make 5 pancakes. Okay? I can't make any more than 5 pancakes because, I only have 2 eggs, even though I might have a lot of flour and a lot of baking powder. If all I have is 2 eggs, all I can make is 5 pancakes. The reason that's useful is because that kind of idea is useful is because now we actually have a conversion factor between eggs and pancakes. Basically, it's 2/5, 2 eggs to 5 pancakes. Or you can flip that. You can say it's five pancakes for every 2 eggs, right? So same idea. We can apply that to the other ingredients. So we can say 1 cup of flour for every 5 pancakes, or 5 pancakes for every 1 cup of flour, and so on. Now, why are those conversion factors useful? Well, that allows us to answer some other questions. For example, let's say I go into my fridge and I see that I have 8 eggs and I have plenty of my flour and baking powder. How many pancakes can I make? Well, we can see that if I have 8 eggs and then I can make 5 pancakes per 2 eggs, you can see how just using simple dimensional analysis, that will tell me that I can make 20 pancakes, right? So you can do it that way or you can just do it in your head. Most people probably will just do it in their head. If I say, hey, I have 8 eggs here, I have plenty of the other ingredients, how many pancakes can I make? You will just tell me it's 20. So it's not really that difficult to do these kind of calculation. And in fact, this is exactly what you're going to be doing when you're dealing with chemical reactions. You're just going to do the same exact type of conversion factor or dimensional analysis calculation that I just did there for the pancakes and the eggs, right? Except that your units is not going to be eggs or pancakes, it's going to be moles, okay? Just like what we did in prior sections when we talk about moles of nitrogen, moles of oxygen, moles of water, etc. So in fact, in chemistry, I think sometimes it's a little easier because the only unit you need to worry about is moles. In cooking, we need to worry about, sometimes we can worry about eggs, sometimes we need to worry about, teaspoon, sometimes we need to worry about cups, right? So there's different units actually in cooking, but in chemistry, it's just one unit, it's just moles, okay? So don't make it more difficult than it is because it is just one unit and all the conversions you need to do is with moles, okay? Let me get to another example here that we can answer with that idea of that conversion factor between, the different components in that equation, right? And so, for example, let's say I tell you I want to make 50 pancakes. How many teaspoons of baking powder am I going to need? Well, again, I can think about using a conversion factor between pancakes and teaspoons of baking powder. So I want 50 pancakes. And then what I need to figure out is, well, what is the conversion factor between pancake and the teaspoon of baking powder? Well, it told us in the recipe that half a teaspoon gives me 5 pancakes. So I can say 5 pancakes, half a teaspoon. So once I do that, cancels away, units cancels away. This is 10 here. So 10 times a half is 5. So I'm going to need 5 teaspoons of baking powder to get 50 pancakes. So I need to go to my pantry and check if I have at least 5 teaspoons of baking powder available, right? And so really, that's the kind of calculation we're talking about in reaction stoichiometry. It's nothing more difficult than that, okay? Now, we're going to apply that same concept that we just talked about with the baking recipe into the calculation with a chemical reaction. Now, in this case, the first thing we need to make sure is we have a balanced chemical equation. This is why you learn to balance first, because unless you have a balanced chemical equation, you don't have a complete recipe. So imagine if all I told you earlier about that baking recipe is I just told you that to make pancakes, you're going to need some flour, some eggs, and some baking powder. Anybody who's done any kind of cooking will ask you immediately, well, how much? How much of each one would I need, right? I know the ingredients, but if I don't know how much, it's not going to be very helpful to make that pancakes, right? You're going to have to try a bunch of times to figure it out, and that's not really useful. And so the first thing you need to make sure is there's a balanced chemical equation, meaning that you need to know exactly how many of each of these species you're going to use and how much you're going to get. The second, of course, is you're going to need the formula of these compounds or elements or ions or whatnot to make sure that you actually have the correct things that you're going to need. Again, I can tell you that if you want to make pancakes, you're going to need some ingredients, but if I don't tell you the specific ingredient to use, you're not going to be able to make the pancake, right? So that's just basic ideas about writing a recipe, or in this case, a chemical equation. you're going to need to put in the state of matter that these chemical species come in, because we want to know, are we supposed to use liquid water or gas water? Are we supposed to use ice? Are we supposed to use hydrogen gas or liquefied hydrogen, right? So there's sort of different states of matter that's going to impact what we're making. Okay, now let's get into the whole recipe idea of this equation that you have in front of it. So I'm going to erase all of these, and let's take a look real carefully how this equation right here, how similar that whole thing is to that baking recipe right there. Okay, so in the baking recipe, I have 3 different ingredients: eggs, flour, baking powder. I make a product called pancake. I have 1 of the flour, 2 of the eggs, and half of a teaspoon of the baking powder. Here, I have 2 ingredients I'm going to need called H2 and N2. I'm going to make my product, which is NH3. And how much of each of these things am I going to need? I'm going to need 3 of that, 1 of this, and then 2 of that. Now, the next thing you need to ask yourself is, what is the unit of these numbers? Okay, earlier we had cups, we have teaspoons. How do we express the unit of these chemical equation? Very simple. All of these are just moles. They're moles. If they're really tiny, if we're counting particles, then we're going to say molecules. But usually we're talking about moles here. So it's 3 moles of H2, 1 mole of N2. Combined together, you're going to make 2 moles of NH3. Okay? And so that's the relationship between all of these species. Now, as we said earlier, now, once we know what the units are, we can write them as conversion factors. So I can say that if I have 3 moles of H2, I'll be able to create 2 moles of NH3. You can flip that. You can say 2 moles of NH3 for every 3 moles of H2. And again, it could be for any one of these species here, just the same exact way as we did earlier with the baking example. Okay, just using that, we'll be able to do some simple calculation right away. Okay, so let's take a look at the first example here. On the top, it says, consider the reaction between sodium metal and chlorine gas to make sodium chloride. Write the balance equation, and then how many moles of NaCl result from the complete reaction of 3.4 moles of Cl2. Okay, so let's write our reaction first. At this point, you should know how to do this. So we'll just write our sodium metal, which is sodium solid. Chlorine gas is Cl2. Remember, chlorine is one of those diatomic gases. And then NaCl is our product. It's a salt, right? And then we're going to have to first balance this out. Balancing here, hopefully, is pretty straightforward. That would give me the balance equation. And so once you have the balance equation, you have your complete recipe. Now you're ready to actually go make things. Okay, you get ready to mix some stuff and make some product. Question here is, how many moles of NaCl would you get when you run a complete reaction with 3.4 mole of Cl2? When they say complete reaction, they just mean that all of the Cl2 is used up. Okay, because you completely get it to the product side. So you're basically asking for how many moles of NaCl, how many product you get if you use up 3.4 mole of Cl2. So this is not too hard to do, hopefully. All you need to do is say, okay, I have 3.4 moles of Cl2, and I want to get myself to the NaCl. Well, what do I need to do? I need to use a conversion factor, mole of Cl2 at the bottom, mole of NaCl at the top. And then what numbers do I put here for the conversion? Well, it's the numbers that you've written as the coefficient. It's this number right here, 2 for NaCl, and then 1 for Cl2. So it's 2 over 1. And then so if you cancel out the units that don't belong, then all you get at the end is 3.4 times 2, which is 6.8 moles of NaCl. Okay? I hope that's easy enough to understand how you can calculate a product quantity based on how much reactant you start with. Okay, I want you to give it a shot for this second problem right here. And then, again, if you're having questions about it, feel free to ask me through email. We just learned how much product we can make based on the chemical equation that we're given, the balanced chemical equation. And we can do it for the product. We can also do it for the reactant, right? So again, don't make this any more difficult than it needs to be. It's the same exact concept as in calculating those recipe type calculation for pancakes, or for, if you're trying to make like different portions of, I don't know, paella or something like that, right? You're going to need to have different things in it, and you need to know exactly how much of each of the ingredient you're going to need. So that's it. That's the extent of the concept that we're dealing with here. Okay, now I'm going to go to the next level of this concept. So the first level, hopefully it's pretty straightforward. The second level now is kind of remembering what we did before with those moles of compounds or elements or whatnot, right? So remember that one of the things we could do back in unit 2 was we could start with moles, and then we can take the moles and then convert them to mass. In order for us to do that, we're going to need molar mass, okay? So we can take our moles of something that we calculate using the approach I just showed you, and we can take that and convert it to the mass of that compound. Same thing here. If we have the mass started with that number, we can then convert it to moles using the molar mass. We learned how to do that back in unit 2. So hopefully that's not too difficult of a leap, right? To understand that once we know how to do these conversions with moles using the chemical equation, I can also take it to mass from there, okay? Now, you might say, why do I care about taking this to mass? Well, the reason is because we don't measure moles. We don't have a tool like a balance or a graduated cylinder or anything like that that directly measure moles of anything, right? What we have, the tools we have, are available to measure masses, balances, scales. Those things can measure masses. Graduate cylinder, burette, other things, those can all measure volumes, but nothing measure moles directly. So we need to convert from what we can measure to something that actually relates to our reaction, which is moles. So moles is what actually is happening in the reaction, but what we can measure is something else. So we need to convert between the thing that we can measure to the thing that's actually happening in the reaction. All right, let's take a look here at this equation. This looks like kind of an intimidating equation. It has 2C8H18. That actually turns out to just be a component of gasoline that we call octane. And then it's being reacted with oxygen gas, and then it produces CO2 and H2O. Now, anytime you react one of these guys here, this is called a hydrocarbon because it has hydrogen and carbon only in it, and you react it with oxygen. This is what we refer to as a combustion reaction. So combustion usually just means you're burning something, okay? You take the gasoline and you burn it. When you do that, you produce CO2 and H2O. So they give you the balance equation, so all those coefficients are there for the different chemical species. And then this is the question they say they want to know, which is they ask you to calculate the mass of CO2 that you emit when you combust 5 times 10 to the second grams of pure octane. That's, 500 grams if you want to make it easier to understand. 500 grams of pure octane generates CO2. How much CO2 is being emitted? Why do we care about this? Well, think about this. This is actually one of the reasons why we worry about global warming, right? Because you are using basically a gasoline here, a fossil fuel, a form of fossil fuel. And whenever you burn any type of fossil fuel, you generate CO2. And CO2, as it turns out, is one of these greenhouse gases that tends to trap heat, and so the amount of heat that's trapped on Earth causes Earth to warm up, and then that causes a lot of additional side effects that we don't want, like, melting of the polar ice caps and so on. So that's sort of going a little far beyond this, but that's the reason why we care about it, okay? Why we want to calculate something like this. But let's get back to the calculation. So we're given 500 grams of this guy, and we want to know, if I have 500 grams of that, how much of this in grams, okay? How many grams of that is produced, right? Because you want to be able to make sure you know how much CO2 you're producing for the process that you're doing. Okay, so how do we do this? Well, steps are pretty easy. First thing we're going to do is we're going to take this guy and we're going to convert it to moles of C8H18. Why? Because remember that equation, all the numbers that are given in that equation, the 2 here, the 25, the 16, and the 18, all of those are moles. They're in units of moles, as I said earlier when I first introduced this idea. Okay, those are all in moles. So unless I have my quantity in moles, I can't do any calculation with that equation. So I first have to convert my grams to moles. Okay, once I do that, then I can take the moles of C8H18 and I can use my balance equation to convert the moles of C8H18 to moles of CO2. Now, this is exactly the calculation we just did earlier with that example with the sodium metal and chlorine gas forming sodium chloride. I did it right here. So look back at that if you had forgotten, but that's exactly what we just did. So all we need to do is just use the equation to help us convert. And then once we have the moles of CO2, we're not done yet because they're asking for mass of CO2. So we need to take this and then convert it back to the mass of CO2. So our final answer. Okay, so a 3-step process. Step 1, step 2, and step 3. Okay, let's see how we can do it. All of these things are things you've learned before. So I'm going to start with that mass to mole conversion. So I want to calculate the moles of C8H18. Well, what do I need here? I'm going to take the 500 grams that I have. And of course, what I'm going to need here is the molar mass of C8H18. You remember that that's a number that we always have to calculate to do any kind of conversion between grams to moles. So here, I'm going to write it. I can multiply. I put the grams at the bottom, the moles at the top, and I could go to the periodic table to look up what this number is. It turns out that this is about 114. Let's call it 114.23 and to 1 mole. So every 1 mole of that gives me 114.23. So if I actually do the calculation, I ended up getting 4.37714 moles of C8H18. Okay, so step 1 is done. I found the number of moles of C8H18. Step 2 is to convert the number of moles of C8H18 to the number of moles of CO2. So let me show you how that works. So the mole of CO2, we're going to take our number of moles that we just found for C8H18, and then we're going to do a little conversion from C8H18 to CO2. Now, what numbers go along here in my conversion factors? Well, it comes from your balance equation. So 16 for CO2 and 2 here for the C8H18. So I'm going to put those numbers there, 16 to 2. Okay? And so if I do that calculation, I ended up getting 35.017 moles of CO2. Step 2 done now. Now the last step, step 3, I have to calculate how much CO2 I actually get in units of grams, i.e. the mass of CO2. So I'll take my 35.017 moles of CO2 and I multiply it by the molar mass of CO2, which is about 44 grams per mole. And when I do that, I ended up getting about 1541. Well, it's 1540.75 grams, which I'm going to write this in scientific notation, and then now I'm going to have to think about the significant figures. Originally, I was given 5.0, so that's a 2 sig fig number. So the answer would be 1.5 times 10 to the third grams of CO2. All right, hopefully that calculation is pretty clear to you, the three different steps that we did there, and how we can get from the grams of one thing to the grams of something else. Now, the steps are worked out here in one shot in the notes, but you can also do it in 3 steps as I showed you. Here they're just combining all those 3 steps in one. So this is step 1, this is step 2, and this is step 3 that I just did. Okay? All right. I'll try to apply that approach that we just did with another one of these problems here. And so let's try, for example, this example, and then you can try the other 2, okay? So with this one, it says NO2 gas, a component of exhaust gases generated by internal combustion engine, reacts with oxygen gas and water to produce nitric acid. That's a typo there. It should have a T, nitric acid, okay? Assume that there's more than enough of the other reactants. How much HNO3 in kilogram forms from 1.5 times 10 to the third kilogram of NO2 pollutant. Okay, so same idea here. Anytime you want to approach these stoichiometry problem, you have to start with a balance equation. Okay, so that's always step number 1. What is your balance equation? I'm going to do this here. Find a little space here to carve out for this. So first, write balance equation. Okay, that's very important. And then second, usually you have to convert to moles. If you don't have it already, you got to convert to moles. Okay? And then third, you usually calculate the moles of that you need. Calculate moles of your unknown. Okay, usually they're asking for some kind of an unknown species, you know, the mass of like something like CO2, for example. Earlier in the previous question, they said mass of CO2. So CO2 is your unknown in that case. The octane in that question was the known. Okay, so convert to moles of known here. Let me just say that. And then calculate moles of unknown. And usually at the end, you have to convert back usually to mass. Convert to mass of unknown. Okay? That's sort of the generic steps that you're going to have to think about. And so in this case, I'm going to start with writing that balance equation. What you need to do is like read that statement carefully and think about what is the actual equation. Well, it says NO2 reacts with oxygen and water to produce nitric acid. So there's 3 things that combine together to produce nitric acid. You're going to need to remember the formula of some of these things from your nomenclature section. So NO2 plus oxygen gas plus water producing nitric acid, HNO3. Okay, so that's the first step. That's just the equation, it's not balanced yet. So now you got to kind of look through this and see if you can balance it. Balancing, as we did before, is a bit of a trial and error. So I'm going to put a 2 here to balance out my hydrogen. That completes that one. And then I'm going to keep this as is for now because the hydrogen is already balanced, so I don't want to change anything about those 2 anymore. Nitrogen now is 2 on the right side, but only 1 on the left side. So I'm going to put a 2 here as well. That means now my nitrogen is also balanced. So the only thing I can touch right now is the oxygen. Let me count how many oxygens I have on both sides. So on the right side, I have 6 oxygen, right? 2 times 3 there. On the left side, I have 4. I have 1, that's 5. And then the middle one is the one I can manipulate if needs be. But right now, it's 2. If I just put a coefficient of 1, that's 2. So 4, 2, and 1. That adds up to 7. On the right side, I only have 6 oxygen. So that means that that O2 in the middle should only be 1 instead of 2. So I only want 1 instead of 2. Now, how do I make 2 become 1? I multiply by a half. Okay? So that means I need to put a half here. Now, as we said before, coefficients can't be fractional. So that means I'm going to just double up everybody's number. Okay, so I'm going to erase all of these things. So this is the balance equation, but I can't have fractional coefficients. So I'm going to go across and say, let me multiply everybody by 2, and that should get rid of my fraction. So I multiply that first number by 2, now it becomes 4. If I multiply half by 2, it becomes 1. So this just don't have to write anything there. And then I multiply 1 by 2, I get 2. And then last one, I multiply 2 by 2, I get 4. Okay, and then at that point, you want to double check real quickly to make sure everything is indeed balanced. And we have how many oxygens now on the left? We have 8 here, we have 2 here, and then we have another 2 here, so that's 12. And then we have 4 times 3, which is also 12. Okay, so everything works out correctly. That's our balance equation then. So let me just erase everything that doesn't belong here so we get a clean balance equation to work with. All right. Now that we have our balance equation, how do we go to the next part of the problem? Well, you have to convert to moles of the node, because remember that the balance equation is only useful if we have units of moles. So let's take a look back at the problem. They say how much HNO3 is formed when we have this much pollutant. So in other words, they told us that we started with this much, we have more than enough of the other reactants, and we're trying to calculate the amount of HNO3. So in other words, we have this. Let me write down exactly the number. It's 1.5 times 10 to the third kilogram. And we want to know how much of that in grams we have. Okay, so the steps are pretty much the same as that problem I was working out with the CO2, which is this problem right here, right? Except that you're going to have to do it for these new species. You're going to have to find their molar masses. So step 1 is you want to calculate the moles of NO2. Okay, so moles of NO2. And the way you calculate that, just like we did earlier, would be to take 1.5 times 10 to the third kilogram. And then you're going to convert that to your moles using molar mass. The problem slightly here is that kilograms, remember, is not the unit of molar mass. The unit of molar mass is grams per mole. So we're going to have to just convert this to grams first. And that's just hopefully not a difficult conversion. Everybody remember this, that kilograms to grams is 1 and 1,000. So now you have it in grams. And then you're going to need to find the molar mass of NO2 in the periodic table. And if you search that up, it should be just around 46. Okay, so it'll be grams at the bottom, moles at the top, 46 to 1. And once you do that, you'll be able to get your molar mass to convert the mass to moles. Okay. And this end up to be a fairly sizable number just because we're starting a pretty big number. But I'm just going to write this out. Okay, so it's 3.2609 times 10 to the 5th moles. Okay, so it's a big number. But, don't round anything right now. You want to keep all your digits around until you get to the very end when you have to round to adjust the significant figures. Once you get the moles of NO2, now the next step is you need to convert that. So you got this part. You need to calculate the moles of the unknown. What unknown are we looking for? Well, we're looking for HNO3, right? And so we're going to have to calculate the moles of HNO3. So we start with the number of moles of NO2. And then we're going to have moles of NO2, and then moles of HNO3. And again, how do I know I put it that way? Because I want to cancel out the NO2. I want to get it to HNO3. And what numbers do I put here? The numbers from the balance equation. So in this case, 4 for HNO3, 4 for NO2. So it happens to be 4 and 4. Okay, 4 and 4. So in other words, the numbers don't change here. We just get the same number, but then the unit changes. The unit changes from moles of NO2, which is what we have, to moles of HNO3. Lastly, we want to know the mass of HNO3. That's really what we're being asked here. And then so we take this number of moles that we just found, and now we're going to bring back our molar mass, but now it's the molar mass of HNO3. So we're going to have to look that up in the periodic table again. And that number is 63 or thereabouts. Let me just write that down. 63 to 1 mole. And so you just take that, multiply by 63, and you end up getting something like 2.054347 times 10 to the power of 6 grams. Okay, this is in grams. Now you can convert it to kilograms and you can fix the significant figure. So originally the numbers we were given was 2 sig figs, 1.5 kilograms. So we're going to just bring that back to that level of significant figure. So the answer would be 2.1, since we're rounding to 2 sig fig, times 10 to the third kilograms. So I changed both the units and the sig fig. So final answer looks like that. Okay, so hopefully that makes sense. I want you to give it a try to the other two examples there. So we have one here, one here. Again, do that. Check that out. See if you get the answer. And then reach out to me and I can confirm whether you get the correct or